Hello there, and welcome to The Sleepless Scientist. Tonight, we set out on a journey into one of the most mysterious corners of the cosmos, black holes. These strange and powerful objects have captured the imagination of scientists and dreamers alike, whispering secrets of gravity, time, and the very fabric of reality. To think of them is to gaze into a paradox, places where matter collapses into infinity, yet where silence and stillness also reign supreme. As we drift into this exploration, allow yourself to let go of the day's concerns. Imagine the quiet of deep space, where stars shimmer faintly and black holes sit like hidden guardians, reshaping everything around them in silence. There is nothing to fear here, only the comfort of curiosity and the calm of wonder. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. What exactly is a black hole? At first glance, the very name seems almost poetic. A hole that swallows light itself. A black hole is not empty space though, but a region where gravity has grown so strong that escape becomes impossible. Matter, once part of a star or a drifting cloud of gas, is pulled inward and compressed to unimaginable density. When we imagine a black hole, it helps to think of it less as a vacuum cleaner and more as a silent, invisible boundary in space. Surrounding it is the event horizon, the invisible line where nothing can return. Inside, the laws of physics bend and twist in ways we still struggle to understand. In truth, black holes remind us of how fragile our human intuitions are. To us, the cosmos seems vast and expansive, but a black hole whispers that there are still places where the universe folds in on itself, revealing mysteries hidden in silence and shadow. How black holes form from dying stars. Let's go back in time to the final moments of a massive star's life. For millions of years, the star burns brightly, its fusion furnace pushing outward against the crushing pull of gravity. But eventually, the fuel runs out. Without the steady push of fusion, gravity wins. The star begins to collapse. Its outer layers may explode outward in a spectacular supernova, but deep inside, the core implodes under its own weight. For smaller stars, this collapse might leave behind a dense neutron star. But if the star is massive enough, the collapse continues until nothing can resist the pull of gravity. A black hole is born. It's a quiet ending and a powerful beginning all at once. From the death of a star emerges something far stranger, a place where time and space bend into shapes our minds can only dream of. Even in destruction, the universe creates new wonders, reminding us of the endless cycle of beginnings and endings. The point of no return, the event horizon. Think about a shoreline where land meets sea. Once you cross into the water, you can still return until the tide carries you past the point where swimming back becomes impossible. For a black hole, this threshold is called the event horizon. The event horizon is not a physical surface. It is an invisible boundary, defined by gravity's strength. Cross this line, and no signal, no light, no particle can escape back into the universe. From the outside, the event horizon appears as a perfect dark sphere. From within, it is the edge of eternity. To imagine standing just beyond the horizon is to feel the tension of cosmic balance. Outside, the universe continues on, full of stars, galaxies, and quiet light. Inside lies a mystery no observer can describe. The event horizon is both a barrier and an invitation, an eternal reminder of how much there is still left to discover. Gravity so strong that not even light escapes. Here's something surprising. Light, the fastest traveler in the universe, racing at nearly 300,000 kilometers per second, cannot outrun the gravity of a black hole. It is pulled inward, its path curved and twisted, until it can no longer find a way out. This is why black holes are invisible, revealed only by their effects. We see stars orbiting something unseen. We watch gas heating and glowing as it spirals inward. We detect gravitational ripples in space-time itself. Yet the black hole, the heart of it all, remains perfectly dark. It is almost poetic to think that the brightest light bows to gravity's silent call. In the calm depths of the cosmos, even light must surrender. And in that surrender, the universe gives us one of its most enduring mysteries, a place defined not by what we see, but by what we cannot. The role of supernovae in black hole birth. Let's pause to consider the grand fireworks that precede a black hole's quiet existence. When a massive star exhausts its fuel, it doesn't simply fade. Instead, it erupts in a supernova, one of the most luminous events in the universe. For a brief moment, a single star can outshine an entire galaxy. In this explosion, heavy elements are scattered into space. Carbon, iron, oxygen, seeds that will one day form planets, oceans, and perhaps even living beings. Yet behind the brilliance, the star's core continues its collapse. If the mass is great enough, no force can halt it, and the remains fall inward, creating a black hole. It is humbling to think that black holes, those silent enigmas, are born from such fiery deaths. Out of chaos comes stillness. Out of blinding light comes perfect darkness. And in that darkness, the universe continues its quiet story. Stellar black holes versus supermassive giants. At first glance, all black holes may seem alike. Dark, silent, invisible. But there are two families, each with its own story. Stellar black holes are the children of dying stars. Their mass is a few times greater than our sun. They are scattered like hidden jewels across the Milky Way, quiet reminders of stars long gone. Then, there are the giants, the supermassive black holes. These titans sit at the hearts of galaxies, weighing millions, even billions of times the mass of our sun. How they formed remains a mystery, but their influence is profound. They shape the growth of galaxies, guiding stars into orbits, feeding on matter, and sometimes blasting jets of energy across light years of space. It is strange to think that the universe carries both the small and the colossal, the quiet remnants of stars and the monsters that rule entire galaxies. Yet both kinds whisper the same truth. Gravity, given time, can shape reality itself into forms that defy imagination. The discovery of black holes in the 20th century. Let's travel back to the early decades of the 20th century. The concept of a black hole was born not from observation, but from equations. Einstein's general theory of relativity, published in 1915, reshaped how we see space and time. Almost immediately, other scientists noticed that his equations allowed for strange solutions, regions of space where gravity collapsed into infinity. At first, these ideas were met with skepticism. They seemed too extreme, too unworldly to be real. For decades, black holes lived mostly in the realm of theory, whispered about by physicists and mathematicians. But slowly, evidence began to build. Stars were observed orbiting invisible companions. X-rays blazed from regions where matter spiraled into unseen voids. By the mid-20th century, black holes moved from speculation to reality. The universe, it seemed, was stranger than even Einstein had dreamed, and the discoveries had only just begun. Why black holes were once just a theory. Think about how unsettling the idea must have seemed at first. A place where light could not escape? A point where matter collapses infinitely? For many years, scientists treated black holes as curiosities of mathematics, not objects of nature. The universe was already mysterious enough. Why add such impossibilities? Even Einstein himself was skeptical. He believed nature would not allow such extremes to exist. But as telescopes improved and the sky revealed its secrets, the evidence became undeniable. Binary star systems showed invisible partners of immense mass. Quasars blazed with energy that could only be explained by supermassive black holes feeding on matter. What was once dismissed as fiction became fact. The lesson is humbling. Sometimes the universe is not only stranger than we imagine, but stranger than we are willing to believe. The first picture of a black hole in 2019. Here's something that feels almost magical. For centuries, black holes were invisible. We could infer their presence, measure their pull, watch their effects, but never see them. Then, in April 2019, the Event Horizon Telescope project unveiled the first image of a black hole's shadow. The object lay at the heart of a galaxy 55 million light-years away, in the constellation Virgo. What the world saw was a glowing ring of light, bent by gravity, circling a perfectly dark center. It was not sharp, not detailed like a photograph of the moon. But it was enough. Proof that the theories were true. Proof that black holes could be seen, not directly, but through the light they warp and devour. That single image, blurry yet profound, connected science and wonder in a way few discoveries ever do. It was as though the universe had, at last, allowed us a glimpse into its deepest secret. The mysterious singularity at the core. At the heart of every black hole lies something we cannot yet fully describe. The singularity. Here, all the matter that fell into the black hole is thought to be compressed into an infinitely small point, a place where density and gravity reach unimaginable extremes. The singularity is more than just a point. It is a boundary for our understanding. Physics, as we know it, breaks down there. General relativity predicts its existence, but quantum mechanics resists, demanding a new theory to explain what truly happens inside. To contemplate the singularity is to stand at the edge of knowledge. Is it really a point of infinite density, or does some new law of nature step in? Does it hold the key to unifying gravity with the quantum world? For now, the singularity remains hidden, silent, unknowable. It is the ultimate mystery at the heart of the universe's most mysterious objects. How black holes bend space and time. At first glance, space seems like a quiet, empty canvas. But near a black hole, this canvas twists and curves in ways that defy intuition. Imagine placing a heavy ball on a stretched sheet of fabric. The fabric dips and bends. This is a simple analogy for how mass warps space. A black hole, however, is far heavier than anything we can imagine, causing a profound curvature that shapes the paths of stars, gas, and light itself. Time, too, is affected. Clocks near a black hole tick more slowly than those far away. A second there can stretch into minutes, hours, or years for an outside observer. This is not fantasy. It is a direct consequence of Einstein's general relativity, a rule of the cosmos written into the very structure of reality. Contemplating this, we begin to see that black holes are not merely empty voids, but sculptors of space-time, warping reality itself and teaching us that our sense of distance and time is not absolute, but woven into the cosmic fabric. Space-time curvature, the fabric of reality. Think about this. Every object in the universe sits on a vast invisible fabric called space-time. Normally, this fabric is nearly flat, stretching gently across galaxies and solar systems. But near a black hole, space-time bends, folds, and steepens into a pit of almost incomprehensible depth. Light, normally traveling in straight lines, curves along these distortions, tracing arcs that can circle the black hole before escaping or failing to escape. Even the planets and stars nearby follow these curved paths, caught in the invisible grip of this warped geometry. By studying this curvature, scientists can map the unseen presence of black holes, predict the paths of stars, and even detect gravitational waves, ripples in space-time that spread across the cosmos, carrying messages from cataclysmic events billions of light-years away. In this way, the bending of space and time is not just theory, it is a language the universe speaks, patiently, silently, and profoundly. Black holes as cosmic vacuum cleaners. Here's something surprising. Despite their fearsome reputation, black holes do not roam the cosmos vacuuming up everything in sight. Their gravitational pull is intense, yes, but only within a certain region. Far beyond their reach, planets, stars, and even entire solar systems continue their orbits almost undisturbed. A black hole only consumes matter that strays too close, crossing the event horizon, the point of no return. Otherwise, it remains a quiet observer, affecting the universe more through gravity and space-time curvature than through indiscriminate destruction. This is a gentle reminder. Even in the darkest corners of the cosmos, nature is measured. Black holes are not cosmic predators hunting blindly. They are guardians of balance, shaping galaxies and stars in ways both subtle and profound, rather than indiscriminately devouring all in their path. Why black holes don't suck everything in? Think about the Earth orbiting the Sun. The Sun's gravity keeps us in a steady dance, yet it does not pull us directly inward. The same principle applies around black holes. If our Sun were replaced by a black hole of equal mass, Earth would continue orbiting safely, oblivious to the danger lurking at the center. A black hole's influence is not an omnipotent vacuum, but a concentration of gravity. Only objects that venture too close, past the invisible boundary of the event horizon, are inexorably drawn in. Beyond that threshold, light, matter, and time itself are trapped. But outside, the universe continues its quiet, elegant rhythms. This distinction reshapes our perception of black holes. They are not destroyers of worlds at a distance, but local anomalies, intense and mysterious, teaching us about the delicate balance between motion, gravity, and cosmic order, the strange physics near the event horizon. Let's go back in time, or rather forward in perspective, to the edge of a black hole. The event horizon is a place where the rules of physics become almost alien to our everyday experience. Light struggles to escape, time slows dramatically, and space itself stretches in strange ways. Here, quantum effects mingle with gravity, producing phenomena that scientists are still striving to understand. Accretion disks glow fiercely as matter heats up, torn apart by tidal forces before vanishing beyond the horizon. And yet, from a distance, the black hole may appear calm, almost serene, a silent sentinel in the cosmic night. To study this region is to peer into the unknown, a frontier where classical physics and quantum mysteries meet. It is a humbling, meditative reminder that the universe contains places so extreme, so foreign, that our imagination can scarcely grasp them, and yet they are very real, waiting quietly to reveal their secrets. Time slows down near a black hole. At first glance, time seems constant, an unyielding river flowing at the same pace for everyone. But near a black hole, this perception unravels. The intense gravity stretches the flow of time, slowing it relative to an observer far away. A minute spent near the event horizon might equal hours, days, or even years for someone observing from a safe distance. This phenomenon is not just theoretical, it is a direct consequence of Einstein's general relativity. Astronauts venturing close would experience a world where the universe outside races ahead, while their own moments feel normal. It is a cosmic lullaby, where gravity's pull orchestrates a subtle dance of time itself, bending reality in ways that challenge our intuition. To imagine this is to glimpse the profound relativity of existence, where even something as familiar as time becomes malleable, stretching and compressing under the influence of the cosmos's darkest objects, the twin paradox and black hole time dilation. Think about two identical twins. One remains on Earth, while the other journeys near a black hole, hovering at the edge of its event horizon. Upon return, the twin who stayed behind may have aged decades, while the one near the black hole has experienced only a fraction of that time. This is known as the twin paradox, and black holes provide a dramatic setting to illustrate it. Here, the fabric of space-time warps so intensely that the passage of time is no longer universal, but deeply relative, dependent on one's position in the gravitational field. The paradox is not just a thought experiment, it reflects real physics. It invites contemplation of time's fluidity, and reminds us that the universe is not an immutable stage, but an intricate interplay of gravity, motion, and perspective, where moments can stretch like elastic threads through the vast cosmic tapestry. Black holes and Einstein's general relativity. Here's something remarkable. Black holes are among the most striking confirmations of Einstein's theory of general relativity. The very idea that mass could warp space and slow time, once a mere equation on paper, finds vivid reality in these cosmic behemoths. General relativity predicts that matter falling toward a black hole will spiral into a deeper gravitational well, stretching light, bending orbits, and distorting time itself. Observations of stars orbiting invisible objects, gravitational lensing, and the ripples of gravitational waves all point to this elegant theory at work. In this way, black holes serve as both crucibles and proof, offering a natural laboratory where our understanding of space, time, and gravity can be tested. They are living monuments to the predictive power of human thought, quietly shaping the cosmos and inspiring endless curiosity. Wormhole theories and black holes. At first glance, the notion of a black hole as a gateway might seem like science fiction, yet in the realm of theoretical physics, some solutions to Einstein's equations suggest that black holes could, under precise conditions, connect distant points in space-time. These hypothetical tunnels are called wormholes. While no evidence yet exists of actual wormholes, imagining them evokes wonder. Could a traveler step through a black hole and emerge light years away, or even in another universe? The equations tantalize the imagination, hinting at paths through the cosmos that defy conventional limitations of space and time. In pondering wormholes, we are reminded of the interplay between theory and possibility. Black holes are not merely destructive forces. They are doorways to questions that stretch the mind, revealing the universe's mysterious capacity for hidden connections. Could black holes be gateways to other universes? Let's go back in thought, beyond our observable cosmos, to the tantalizing possibility that black holes might bridge to entirely separate universes. Some speculative theories propose that the singularity within a black hole could pinch space-time into another realm, creating a passage to a universe with its own laws, stars, and perhaps life. While no empirical evidence supports this, the concept invites quiet reflection. It suggests that what appears as an ending, a point where matter and light vanish, might be a beginning elsewhere, a seed for a new cosmos. Black holes, in this light, are not merely voids, but symbols of cosmic mystery, portals to the unknown, and reminders of how much remains beyond our reach and understanding. To contemplate such possibilities is to embrace both humility and awe, recognizing that the universe holds realms of beauty and enigma, where imagination and science entwine in the endless dance of discovery. Spaghettification. What happens if you fall in? At first glance, the phrase spaghettification sounds almost whimsical, yet it describes one of the most extreme experiences the universe can offer. As you approach a black hole, gravity's pull stretches unevenly. Your feet, if nearer the singularity, feel a far stronger tug than your head. Slowly, your body would elongate, narrowing into a thin, stretched form, like a cosmic noodle. This phenomenon is a vivid illustration of tidal forces, the gradient of gravity across your body. It is a stark reminder that near a black hole, familiar rules of scale and comfort vanish. While no human has ventured this close, physicists use the concept to understand how matter behaves under extraordinary stress. In imagining spaghettification, we confront both fear and fascination, recognizing how delicate our terrestrial existence is. The universe, in its extremes, teaches us about limits, resilience, and the dramatic, awe-inspiring ballet of physics in its rawest, most uncompromising form: accretion disks. Rings of fire around black holes. Here's something mesmerizing. Black holes, though invisible themselves, often announce their presence with spectacular rings of light known as accretion disks. These disks form as matter spirals inward, compressed and heated by immense gravitational forces, until it radiates brilliantly across the electromagnetic spectrum. The swirling matter emits X-rays and visible light, creating a luminous halo that hints at the dark heart within. It is as if the black hole, an object defined by absence, manifests through the energy of everything it draws near. Observing these disks offers astronomers a way to study the invisible, mapping the influence of gravity in extraordinary detail. Accretion disks remind us that even in darkness, there can be beauty, movement, and light. The cosmos balances extremes, where destruction and brilliance coexist, and where the quiet pull of gravity sculpts some of the most stunning structures imaginable. How matter heats up near a black hole. Think about matter falling into a black hole as a dancer approaching a powerful center. The closer it gets, the faster it moves, friction increasing as particles collide in a frenzied spiral. Temperatures soar to millions of degrees, hotter than the cores of stars, causing radiation to blaze outward even as the ultimate destination remains unseen. This heating process not only fuels the accretion disk's brilliance, but also powers some of the most energetic phenomena in the universe. X-rays and gamma rays escape the outer edges, while the black hole itself remains shrouded in mystery. It is a cosmic paradox. The closer to darkness, the brighter the light. By studying these processes, scientists can infer mass, spin, and behavior of black holes, turning indirect observations into profound understanding. Matter, in its final dance, becomes both a messenger and a spectacle, narrating the story of a region we can feel, but never directly touch. The brightest lights come from the darkest places. Here's something quietly beautiful. The universe often paradoxically reveals its most luminous spectacles in its darkest corners. Near a black hole, matter, compressed and heated to unimaginable levels, radiates light that can outshine entire galaxies. The void itself becomes a stage for cosmic fire. These lights, though born from destruction, illuminate the fundamental mechanics of the universe. Jets of energy and radiation arc through space, sculpting surroundings, and signaling to distant observers that something extraordinary lurks in the void. Even in regions defined by absence, nature finds a way to express brilliance. This interplay of darkness and light reflects a deeper cosmic poetry. It reminds us that in mystery and obscurity, there is potential for revelation, and that even the most forbidding places can inspire awe, curiosity, and quiet wonder as we peer into the universe's hidden corners. Quasars, powered by supermassive black holes. Let's go back in time to when the universe was young, and some of its brightest beacons were already blazing. Quasars, powered by supermassive black holes at galactic centers, shine with an intensity that dwarfs entire galaxies. Matter falling into these giants releases tremendous energy, creating visible and radio light that travels billions of light years to reach us. Quasars are both time capsules and cosmic lighthouses, illuminating the early universe while revealing the immense influence of black holes. Their light, constant yet fleeting in human perception, carries the signatures of gravity, motion, and matter's final surrender. In witnessing quasars, we appreciate that even the darkest hearts of the cosmos can generate extraordinary beauty. They are reminders that in the universe, creation and destruction are inseparably intertwined, and that light, born from the brink of oblivion, can illuminate the vast tapestry of space and time. The role of black holes in galaxy formation. At first glance, black holes seem like mere consumers, devouring everything in their vicinity. Yet, paradoxically, they play a vital role in the shaping of galaxies. Their immense gravity helps anchor stars, gas, and dust, guiding the motions of countless cosmic bodies over eons. During their growth, black holes can regulate star formation. Powerful jets and radiation can either ignite new stellar nurseries by compressing gas clouds, or prevent stars from forming by heating and dispersing the material. This delicate balance ensures that galaxies evolve in structured, yet dynamic ways. Observing black holes in this context transforms our understanding of cosmic architecture. They are not just destructive voids, they are sculptors of matter, orchestrating rhythms of growth and decay across the galactic canvas. In their quiet dominion, they influence the lives of billions of stars, including, indirectly, our own sun. Every large galaxy has a black hole at its core. Here's a humbling fact. Nearly every massive galaxy harbors a supermassive black hole at its center, a silent conductor behind the cosmic symphony. From spiral galaxies like our Milky Way to distant elliptical giants, these dark anchors are ubiquitous, shaping rotation, stellar distribution, and overall structure. Their presence suggests a deep intrinsic link between black holes and galaxy formation. Galaxies without such a central mass are rare anomalies. By measuring orbital speeds and emissions from surrounding matter, astronomers detect these invisible giants and map their influence across millions of light years. Understanding this connection brings perspective. Even as galaxies evolve, merge, and fade, the black holes at their cores endure, quietly guiding the cosmic dance, a hidden pulse beneath the luminous beauty of countless stars. The monster at the center of the Milky Way. Let's go closer to home. Deep within the Milky Way lies a supermassive black hole, Sagittarius A, a cosmic leviathan, weighing roughly 4 million suns. Though invisible, its presence is betrayed by stars orbiting at dizzying speeds in clouds of gas, heated to extreme temperatures. Sagittarius A exerts a gravitational authority that defines the inner galaxy. Its quiet, enduring influence stabilizes our celestial neighborhood, providing a backbone around which billions of stars revolve in complex harmony. Observations using radio and infrared telescopes reveal its subtle movements, hinting at a dynamic entity rather than a static void. In imagining this monster at the center of our home galaxy, we confront both intimacy and vastness. We are close enough to measure its influence, yet far enough to feel the staggering scale of cosmic time and space, a reminder of our place in the quiet majesty of the universe. Sagittarius A and our galactic neighbor. Here's something to ponder. Sagittarius A is not just a distant concept, it is a neighbor whose pull we feel through the slow, rhythmic orbits of nearby stars. Each star's path is a storyteller, tracing invisible lines of gravity around this immense center. Its influence extends far beyond immediate proximity, shaping the spiral arms, guiding interstellar clouds, and subtly affecting planetary systems like our own. Studying these motions allows astronomers to map the dark heart of the Milky Way, revealing details about mass, density, and the intricate dance of galactic matter, even as we gaze toward it from tens of thousands of light-years away. Sagittarius A Calypso connects us to a living galaxy, reminding us that the unseen and the observable are entwined, and that the cosmos often speaks in quiet, gravitational whispers. How black holes collide and merge. Think about the colossal drama that unfolds when two black holes meet. Guided by gravity, they spiral ever closer in a silent, invisible waltz, moving faster as they lose energy in the form of gravitational waves. The final collision is cataclysmic, merging into a single, even more massive black hole, sending ripples through the fabric of space-time. These mergers are not just theoretical. Detectors like LIGO have captured the faint tremors of these distant cosmic dances, allowing us to hear the universe in a way invisible to the eye. The events reshape galaxies, redistribute energy, and remind us that even in darkness, motion and change persist. Collisions of black holes are cosmic punctuation marks, marking endings and beginnings. They reveal the dynamic nature of the universe, where even the most incomprehensible forces move to patterns of order, echoing across billions of light-years, and reminding us of the restless creativity inherent in the cosmos. The ripples of gravity, gravitational waves. At first glance, space seems silent, a vast emptiness stretching without sound. Yet, when massive objects like black holes accelerate or collide, they send ripples through the very fabric of space-time. These ripples, known as gravitational waves, propagate across the cosmos at the speed of light, stretching and compressing space ever so slightly as they pass. Albert Einstein predicted their existence over a century ago, and for decades, they were an unseen whisper of the universe. Gravitational waves carry information about the most violent and energetic events, revealing the masses, spins, and distances of black holes and neutron stars. Each detection allows astronomers to peek into phenomena otherwise invisible, turning the quiet void into a cosmic symphony. Listening to these waves reminds us of the subtle interconnectedness of the universe, though imperceptible to our senses. The collisions of distant black holes create vibrations that reach us, bridging unimaginable distances and inviting contemplation of both the fragility and grandeur of space-time itself. LIGO's first detection of black hole mergers. Here's a moment that reshaped modern astronomy. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, recorded the first direct evidence of two black holes merging. The signal, faint but unmistakable, was a tiny distortion in the fabric of space-time, as if the universe itself had whispered across billions of light-years. This groundbreaking detection confirmed Einstein's century-old prediction and opened a new era of astronomy. For the first time, we could observe the universe not just with light, but through its gravitational rhythm. Each subsequent detection has expanded our understanding of black holes, their frequency, and their cosmic choreography. The significance is profound. It proves that even the darkest, most hidden objects announce their presence in subtle ways, and that the cosmos, in its vast silence, is constantly communicating through patterns we are only beginning to interpret. Black hole mergers are the loudest events in the universe. Think about this. When black holes collide, the energy released is stupendous, exceeding the combined light output of all stars in the observable universe, albeit in gravitational waves rather than visible light. Though imperceptible to our eyes, these events are the loudest phenomena known to science, sending tremors through the cosmos. The sound of a merger encodes details about the mass, spin, and dynamics of the black holes involved. Each ripple carries a story of colossal forces, of objects so dense that not even light can escape, yet whose influence radiates outward, detectable across billions of light years. In reflecting on these events, there is both awe and serenity. The universe operates on scales far beyond daily human experience, yet through careful observation, we tune into the hidden rhythms of creation and destruction, finding a quiet, contemplative joy in understanding the most extreme reaches of reality. Intermediate mass black holes, the missing link. Here's something subtle but compelling. Between stellar mass black holes and the supermassive giants lie intermediate mass black holes, mysterious entities that bridge the cosmic spectrum. They are elusive, rarely detected, and may hold clues to the formation of galaxies and the growth of their central black holes. Scientists search for these hidden giants by observing gravitational interactions with nearby stars and the faint X-ray glow from accreting material. Each candidate detection raises tantalizing questions. How do these mid-sized black holes form? Could they be remnants of dense star clusters or seeds for future supermassive black holes? Pondering these questions invites reflection on the universe's subtle architecture. Even in the vast darkness, patterns emerge, and discoveries of these intermediate mass black holes remind us that there are layers of complexity we are only beginning to perceive, hidden in the quiet corners of space-time. How scientists find invisible black holes. At first glance, black holes are invisible, cloaked by their own gravity, yet their presence is betrayed by their effects on nearby matter. Stars orbiting unseen masses, hot gas swirling in accretion disks, and gravitational lensing bending the path of light all reveal their hidden dominion. Astronomers employ X-ray and radio telescopes, gravitational wave detectors, and precise measurements of stellar motions to infer the presence of these elusive giants. By studying their interactions with the environment, scientists map their influence, revealing the invisible scaffolding around which galaxies form. The search for black holes blends patience, ingenuity, and wonder. It demonstrates that even in emptiness, there is substance, patterns, and meaning. In following these invisible behemoths, we discover a universe that is both mysterious and intimate, whispering stories of creation, destruction, and the quiet, unseen forces that shape all we observe. Gravitational lensing. Black holes as cosmic magnifiers. At first glance, a black hole seems like a void, a region where light cannot escape. Yet, in a beautiful cosmic irony, black holes can also magnify the universe around them. Through the phenomenon of gravitational lensing, the immense gravity of a black hole bends and distorts the light from distant stars and galaxies behind it, producing arcs, rings, and multiple images of the same celestial objects. This bending of light allows astronomers to peer farther into space, revealing galaxies that would otherwise remain hidden. The black hole, a symbol of darkness, becomes a lens of illumination, an unintentional telescope crafted by gravity itself. Through these distorted images, we witness the interplay of mass and light, the subtle warping of space-time that makes the universe feel both intimate and infinite. The quiet elegance of gravitational lensing reminds us that even objects associated with destruction can create beauty, offering a lens not only into distant space, but also into the poetic balance underlying cosmic forces. The shadow of a black hole explained. Here's something extraordinary. A black hole casts a shadow. In 2019, the Event Horizon Telescope captured the first ever image of this shadow, revealing the dark silhouette of a supermassive black hole against the glowing halo of its accretion disk. The shadow itself is not the black hole, but the boundary where light is trapped by its gravity. This shadow offers more than a picture. It provides a test of Einstein's general relativity under extreme conditions. Its circular shape and size reveal the mass and spin of the black hole, turning a feature once purely theoretical into observable reality. Reflecting on this image evokes a quiet awe. We see the intersection of light and dark, the boundary between the known and the unknown. The black hole's shadow reminds us of the limits of perception, and yet of the human capacity to stretch understanding into realms once thought inaccessible. Black holes can spin at near light speed. Think about this. Black holes are not merely static voids. Many rotate at astonishing speeds, close to that of light itself. This spin twists space-time, dragging it around in a phenomenon known as frame dragging, creating swirling maelstroms of energy and warped orbits around them. A spinning black hole can influence the shape of its accretion disk, the direction of jets, and even the fate of stars nearby. The angular momentum inherited from its progenitor star or accumulated over cosmic time gives it a dynamic presence, a cosmic whirlpool silently shaping its surroundings. Contemplating such rotation brings both serenity and wonder. The universe is not only vast and empty, but alive with motion, subtle yet immense, reminding us that even in darkness there is structure, rhythm, and a hidden dance that persists across billions of years. The difference between rotating and non-rotating black holes. At first glance, all black holes might seem similar, infinitely dense, inescapable, mysterious, yet their spin changes everything. Non-rotating, or Schwarzschild, black holes are simple in structure, their event horizons perfectly spherical, their influence uniform. Rotating, or Kerr, black holes, by contrast, drag space-time around them, producing an oblate shape, warping orbits, and twisting the path of infalling matter. This difference has profound implications. Rotating black holes can sustain energy extraction mechanisms, powering relativistic jets that shoot across galaxies. They can also alter the dynamics of nearby stars, influencing the evolution of star clusters and even the growth of galactic cores. By understanding rotation, we glimpse the subtle diversity within cosmic phenomena. Black holes are not merely singularities. They are dynamic participants in the universe, each with a unique rhythm and impact, silently shaping the cosmos while remaining forever beyond our direct touch. Kerr black holes, when rotation changes everything. Here's something extraordinary. Kerr black holes, named after the mathematician Roy Kerr, reveal that rotation transforms the nature of space-time itself. Around these spinning giants, the event horizon and the ergosphere create regions where nothing is stationary, where even space is dragged along, swirling in a cosmic dance. Inside the ergosphere, it is theoretically possible to extract energy, a phenomenon that fascinates both physicists and dreamers alike. The equations governing Kerr black holes predict paths and motions unimaginable, with stable and unstable orbits, frame-dragging effects, and the potential for exotic phenomena like Penrose processes. Contemplating a Kerr black hole invites reflection on the complexity underlying simplicity. From a distance, it is just a shadow in space, a silent observer. Yet its spin turns emptiness into a stage of cosmic motion, a living example of the universe's ability to blend beauty, mystery, and physics into a single quiet enigma. Charged black holes and their peculiar physics. At first glance, a black hole seems simple: mass, gravity, and an event horizon. Yet some black holes carry electric charge, creating fascinating distortions in the surrounding space-time. These charged black holes, described by the Reissner-Nordström solution in general relativity, exhibit properties far stranger than their neutral cousins. The presence of charge modifies the gravitational pull and introduces additional horizons, creating regions where light and matter follow entirely different paths. The electric field interacts with incoming particles, subtly shaping accretion and sometimes producing phenomena that are almost alien in their complexity. Thinking of a charged black hole evokes quiet wonder. It is a reminder that even in darkness, subtle forces persist, sculpting reality in ways both predictable and mysterious. Charge adds another layer to the cosmic narrative, hinting that black holes, while often imagined as simple voids, are in fact intricate laboratories of the universe, quietly testing the laws of physics at their extremes. Black holes evaporating, Hawking radiation. Here's something truly poetic. Black holes, the ultimate consumers of matter and light, are not eternal. In the 1970s, Stephen Hawking proposed that quantum effects allow black holes to emit radiation, slowly losing mass over unimaginable timescales. This radiation, now called Hawking radiation, arises from the flickering of virtual particles near the event horizon. The process is subtle and slow, almost imperceptible against the vastness of cosmic time. A small black hole could eventually evaporate completely, leaving nothing behind but a whisper of energy. This idea challenges our intuition, reminding us that even the most extreme objects are subject to change, impermanence, woven into the fabric of existence. Hawking radiation is a delicate bridge between quantum mechanics and general relativity, offering glimpses of a deeper understanding of the cosmos. In its quiet, inevitable glow, we see a universe where even darkness has a life cycle, a slow fading that is both humbling and strangely comforting. Why black holes aren't eternal? Think about eternity, and the image of a black hole often comes to mind. Infinite, unchanging, a cosmic monument. Yet, through the lens of modern physics, black holes are impermanent. Hawking radiation slowly saps their mass, while collisions and interactions can further alter their existence. Even supermassive black holes, which anchor galaxies, will one day face decay over timescales far beyond our imagination. This notion introduces a gentle humility into our understanding of the universe. Nothing, not even these titanic voids, escapes change. The cosmos is alive with impermanence, cycles of formation and destruction that echo across billions of years. Considering black holes' eventual evaporation invites reflection on the fleeting nature of all things, even in the vastness of space. It is a serene reminder that the universe, in all its grandeur, is a dynamic, evolving canvas, where even the darkest regions eventually yield to the subtle flow of time. Black hole thermodynamics, heat and entropy. Here's something intriguing. Black holes have temperature and entropy. The connection, first proposed through the work of Bekenstein and Hawking, reveals that black holes obey a form of thermodynamics. Their entropy is proportional to the surface area of the event horizon, not the volume inside. A remarkable departure from everyday experience. This relationship links gravity, quantum mechanics, and information theory in a quiet dance of elegance. As black holes radiate and lose mass, their entropy changes, highlighting a subtle bookkeeping of energy and information in the universe. The laws of thermodynamics apply even in these extreme conditions, turning a seemingly simple void into a stage for cosmic order. Contemplating black hole thermodynamics invites both awe and calm. It is a reminder that order and law persist even where chaos seems absolute, that the universe has a hidden structure beneath the surface of darkness, and that every black hole, in its silent existence, reflects a quiet balance of cosmic principles. Information lost in a black hole. At first glance, a black hole seems to swallow everything without a trace. Matter, energy, and even information appear to vanish beyond the event horizon. Yet quantum mechanics insists that information cannot truly be destroyed, leading to one of the deepest puzzles in modern physics, the black hole information paradox. Could the information about the matter that falls in be preserved in subtle correlations of Hawking radiation, or does it somehow escape through unknown mechanisms? This paradox challenges our understanding of reality itself, blurring the line between certainty and mystery. Reflecting on this question evokes a profound sense of humility. Even as we develop ever more sophisticated theories, black holes remain a reminder of the universe's depth and subtlety. In the silence of these cosmic shadows, we confront the limits of knowledge, yet also the quiet thrill of discovery and the comforting notion that mystery is a natural and eternal companion of exploration. Could the universe be a giant black hole? Let's go back in time and imagination. Some theorists have speculated that our universe itself might resemble a black hole, expanding from a singularity in a manner reminiscent of the event horizons we study. This idea bridges cosmology with black hole physics, suggesting that the birth of our cosmos, the Big Bang, could share properties with the collapse of a massive star. In this view, the universe is both a laboratory and a mirror of black hole behavior. While the notion is largely speculative, it invites reflection on scale and perspective. Black holes, usually considered small pockets of extreme gravity, echo in the very fabric of our cosmos, hinting at connections that stretch across time and space. This concept, quiet and contemplative, invites awe. It is a reminder that the universe might hold structures and symmetries far beyond our current understanding, that even the vast emptiness around us could resonate with the hidden geometries of cosmic creation. The idea of primordial black holes. Here's something intriguing. Black holes might not all be born from dying stars. Primordial black holes, theorized to have formed in the first moments after the Big Bang, could have emerged from dense fluctuations in the young universe. These ancient voids, if they exist, carry whispers of a time before stars and galaxies. Primordial black holes could range from microscopic to massive, potentially influencing galaxy formation or even contributing to the dark matter puzzle. They are silent witnesses to the early universe, reminders that history is written not only in light and matter, but in the shadows and gaps between. Thinking of these ancient black holes evokes a calm curiosity. They are cosmic fossils, quiet and enduring, offering subtle clues to the universe's infancy, and their possible existence encourages us to explore realms where observation meets imagination. Microscopic black holes in quantum theories. At first glance, a black hole is immense and unstoppable. Yet some quantum theories predict the existence of tiny microscopic black holes born in high-energy conditions or particle collisions. These objects, smaller than atoms, would evaporate almost instantly via Hawking radiation, leaving brief traces of energy. Microscopic black holes remind us that the universe operates across a spectrum of scales, from the unimaginable vastness of supermassive black holes to infinitesimal pockets of curvature in space-time. They are fleeting, almost ghostly, yet they challenge our understanding of how gravity and quantum mechanics intertwine. Contemplating them brings a soothing sense of wonder. Even in the smallest corners of reality, the universe crafts extraordinary phenomena, quietly bridging the very large and the very small, revealing that complexity can hide in the subtlest folds of existence. Do black holes lead to the multiverse? Here's something to ponder as the night deepens. Could black holes connect to other universes? Some speculative theories suggest that the singularity inside a black hole might open pathways to new budding universes, each expanding beyond the reach of our own. While evidence is lacking, the idea is a poetic one. Black holes, often imagined as endings, might instead be seeds of creation, gateways to realms unseen. In this vision, the cosmos becomes a branching network of possibilities, where each black hole quietly contributes to an endless cosmic tapestry. Thinking in this way evokes calm and awe. It encourages us to see black holes not as destructive voids, but as contemplative monuments, perhaps offering glimpses of infinity, reminding us that the universe is far more mysterious and far more gentle in its hidden rhythms than our day-to-day experiences suggest. The firewall paradox, a cosmic mystery. At first glance, the firewall paradox is unsettling. If quantum mechanics holds, an infalling observer might be incinerated by high-energy particles at the event horizon, yet general relativity insists the horizon should feel smooth. This conflict is one of the deepest puzzles in theoretical physics. It is a paradox that invites quiet reflection rather than immediate answers. It reminds us that even in the most extreme environments, the universe's behavior can challenge intuition, inviting humility and curiosity. The paradox is a gentle whisper of mystery, suggesting that our understanding is incomplete, that the cosmos preserves its secrets in subtle, intricate ways. The firewall paradox, in its silent tension, evokes awe. It reminds us that the universe holds questions without easy answers, that mystery is an eternal companion to knowledge, and that in pondering these enigmas, we participate in a timeless dance with the cosmos itself. Can anything escape a black hole? At first glance, black holes seem like ultimate prisons, places from which nothing can emerge. Light, matter, even time itself is said to be trapped once past the event horizon. Yet physics offers subtle nuances. Hawking radiation, a gentle glow predicted by quantum mechanics, allows black holes to lose mass over eons. This means that, in a way, a whisper of what falls in can re-emerge, not as the original object but as energy transformed. It's a quiet, almost meditative reminder that the universe has layers of complexity, that even the most absolute-seeming endings can harbor subtle processes beyond immediate perception. Contemplating this evokes a calm humility. Black holes, while immensely powerful, are not completely beyond comprehension. They teach us about limits, about transformation, and about the beauty inherent in a cosmos that never truly lets anything vanish without trace. White holes, the opposite of black holes? Here's something surprisingly poetic. If black holes draw everything in, white holes might do the opposite, expelling matter and energy. Though purely theoretical, white holes offer a mirror to the quiet gravity of black holes, as if the universe itself balances intake and outflow, creation and consumption. They exist in equations and imagination rather than observation, yet the idea evokes gentle wonder. One can picture a celestial fountain, silent and majestic, releasing energy into the void. White holes remind us that physics sometimes allows for symmetry, that the universe can be both mysterious and elegant in its possibilities. Reflecting on white holes is calming. They are conceptual reminders that the cosmos might operate with poetic consistency, that for every inward pull there may be an unseen, graceful outward motion waiting to be discovered. The link between black holes and dark energy. Think about this. Black holes, the densest pockets of matter, and dark energy, the subtle force pushing the universe apart, may share a deeper connection. While distinct in function, both influence the large-scale behavior of the cosmos, shaping galaxies and the expansion of space itself. Some theories speculate that black holes could contribute to the effects attributed to dark energy, or that dark energy might influence black hole dynamics over cosmic time. The details remain uncertain, yet the contemplation of such links invites quiet fascination. It reminds us that even extreme phenomena are not isolated, but threads in a vast cosmic tapestry. In this reflective view, black holes are not merely destructive, they are participants in a subtle, universe-spanning equilibrium, influencing the gentle expansion of space and the unfolding story of cosmic time. The link between black holes and dark matter. Here's something intriguing. Black holes, though invisible, exert enormous gravitational pull, and dark matter, unseen yet pervasive, shapes galaxies. Could there be a subtle interplay between these two enigmatic entities? Perhaps black holes anchor clumps of dark matter, or perhaps dark matter influences black hole growth. Though much remains speculative, the idea is comforting in its elegance. Two mysteries of the cosmos might dance together, hidden from sight, yet orchestrating the motion of stars, galaxies, and the very structure of space itself. It's a quiet cosmic choreography, unfolding slowly over billions of years. Reflecting on this evokes a gentle sense of connection. Even phenomena that seem extreme, isolated, or incomprehensible are part of a broader, harmonious universe, reminding us of the beauty in unseen relationships. Black holes as cosmic engines. At first glance, black holes may seem destructive, but they can also be seen as engines, driving motion, shaping galaxies, and powering the luminous quasars we observe across vast distances. Matter spiraling into a black hole can release tremendous energy, sometimes outshining entire galaxies in brilliant displays. In this way, black holes transform consumption into creation. Their influence is quiet yet immense, regulating star formation and sculpting the cosmic environment. Thinking of them as engines highlights the balance of forces in the universe, the delicate interplay between gravity, energy, and motion. Contemplating these cosmic engines is soothing. They remind us that even in darkness, there is purpose and beauty. The universe is not chaotic, but ordered in its quiet rhythms, where destruction becomes creation, and the most enigmatic objects contribute to the grand, ongoing story of existence. How black holes shape the life of stars. At first glance, black holes may appear as silent consumers, waiting for stars to drift too close. Yet their influence is subtle, pervasive, and quietly transformative. When a star passes near a black hole, tidal forces can stretch and pull it, stripping away outer layers, and sometimes triggering bursts of light that ripple across space. This interaction is not merely destructive, it can shape the distribution of stars within galaxies, guiding their orbits and influencing the density of star clusters. By regulating where stars survive and how they move, black holes act as unseen choreographers, arranging the cosmic dance with invisible hands. The thought of such silent governance evokes a calm reflection. Even objects as extreme as black holes participate in a universe of order, suggesting a balance between chaos and structure. Stars live their luminous lives, and in quiet ways, black holes ensure the ongoing rhythm of the cosmos, reminding us that even in apparent darkness, there is a subtle nurturing presence, jets of energy, blasted by black holes. Here's something surprising. Black holes, often imagined as inescapable voids, can also emit tremendous jets of energy, stretching across light years of space. These jets are born from the swirling accretion disks around the black hole, where friction and magnetic forces accelerate particles to near light speed. The spectacle is both violent and mesmerizing. Streams of matter are ejected outward, shaping galaxies and influencing star formation. Far from being passive, Black holes can actively sculpt their surroundings, lighting up the darkness in spectacular, almost painterly ways. Observing these cosmic jets invites a meditative wonder. The universe, through black holes, demonstrates that power can coexist with beauty. These energetic outflows, invisible to the naked eye, yet monumental in scale, remind us that the cosmos is alive with subtle drama, a theater where even the darkest actors have their luminous roles. Black holes feeding versus starving. Think about this. Black holes are not always ravenous. Some actively consume nearby gas and dust, creating luminous accretion disks visible across millions of light years, while others lie dormant, quietly waiting in the shadows. This cycle of feeding and starvation is gentle in its rhythm, unfolding over millions or billions of years. The variability is calming when considered slowly. A black hole may dominate its galaxy for a time, then fade into quietude, leaving the surrounding stars and gas untouched. The universe, in this view, is patient and deliberate, allowing immense objects to oscillate between activity and rest, teaching us that even extremes have their pauses and cycles. Reflecting on these periods of dormancy encourages a meditative awareness. Life, like the cosmos, includes intervals of intensity and stillness, and even the most powerful forces in the universe experience quiet, measured cycles that sustain the greater cosmic balance. Dormant black holes, waiting in the dark. Here's a serene image. Black holes lying in wait, invisible, silent, yet immensely powerful. Dormant black holes are like cosmic seeds, resting quietly until circumstances bring matter close enough to awaken their energy. For billions of years, they remain hidden, their presence inferred only by subtle gravitational effects on nearby stars. This quiet patience is astonishing, unlike the sudden brilliance of an active black hole. These dormant giants embody a calm permanence. They remind us that immense power does not always manifest loudly, that the universe often operates in subtle, almost imperceptible ways. The thought evokes a gentle reflection on hidden potential and unseen influence. Much like the quiet presence of a sturdy tree or a calm river, dormant black holes shape the cosmos in ways that are not immediately visible, demonstrating that stillness can be as meaningful as motion and that the universe often works through quiet, patient forces. Could a black hole destroy Earth? At first, such a question feels alarming, but the reality is soothing in its perspective. The nearest known black holes are hundreds or thousands of light years away, their gravity too distant to influence our solar system. Earth will never be consumed by one in our cosmic neighborhood. Yet pondering the theoretical possibility offers a reflective exercise in scale. Black holes remind us of the vastness of the universe, the patience of cosmic time, and the resilience of our small world amidst immense forces. We are safe, floating through space while galaxies spin and black holes silently shape the motion of stars far beyond our reach. Thinking calmly about such extremes can be meditative. The universe includes forces of unimaginable power, yet they do not intrude on our daily lives. Black holes, in this sense, are reminders of our place within a larger cosmos, inspiring awe and humility without immediate danger, allowing the mind to wander gently through the quiet majesty of the stars. The distance to the nearest known black hole. Let's take a quiet journey through space to the nearest known black hole, a silent giant, hundreds of light years away. Though immense in mass, its distance provides a comforting perspective. From our vantage point on Earth, it exerts no influence on our planet, allowing us to admire its existence as a gentle reminder of the cosmos's scale. Even at such a distance, scientists can detect its presence by observing the motion of nearby stars, feeling the subtle tug of gravity. These measurements are delicate, almost poetic in their precision, like sensing the heartbeat of an invisible friend across a vast room. Reflecting on this distant neighbor encourages a calm awareness of cosmic proportions. The universe holds immense forces, yet they coexist peacefully with our own little world. The nearest black hole is both a humbling and reassuring presence, a reminder that even the most powerful objects can remain distant, silent, and almost meditative in their influence. Wandering rogue black holes in space. Here's something extraordinary. black holes that wander alone through the galaxy, untethered to stars or clusters. These rogue black holes drift silently, invisible to the eye, their journeys spanning millions of years, unhurried and calm. Though their power is immense, their motion is graceful, a testament to the quiet, measured rhythms of the universe. They may pass near star systems, bending or nudging matter subtly, leaving behind traces that can only be detected through careful observation. Imagining such solitary travelers evokes a meditative reflection. In a universe bustling with energy and motion, some forces move slowly, almost imperceptibly, tracing paths that stretch across cosmic distances. Rogue black holes remind us that even in solitude, there is purpose and motion, a quiet elegance in the silent dance of matter and gravity. Stellar mass black holes throughout the Milky Way. At first glance, our galaxy seems serene, with stars scattered like soft lights across the velvet sky. Yet sprinkled among them are stellar mass black holes, remnants of massive stars that once burned brilliantly. These objects are hidden, their gravity shaping the orbits of nearby stars and whispering secrets of past stellar lives. Despite their invisibility, their presence is profound. Each black hole tells a story of stellar birth, life, and death, a reminder that endings are often as beautiful and necessary as beginnings. They punctuate the Milky Way with quiet significance, silently shaping the rhythm of our galaxy. Thinking of these scattered giants inspires a gentle awe. Even in the midst of our daily routines, we are surrounded by forces that have persisted for millions of years, quietly guiding the motions of stars and reminding us of the subtle yet immense power woven throughout the cosmos. Ultramassive black holes at the edge of reality. Here's something truly humbling. Ultramassive black holes residing at the centers of galaxies, with masses billions of times that of our Sun. These cosmic titans anchor galaxies, shaping their form and influencing the evolution of countless stars. Despite their enormity, they remain distant, their influence measured and precise. These giants do not rush. They grow slowly, feeding on gas and dust, sculpting the galactic environment over eons. Their presence evokes a calm, reflective wonder. In their quiet persistence, ultramassive black holes embody the patient rhythms of the universe, demonstrating that even the most powerful forces operate in harmony with cosmic time. Considering their scale encourages a meditative awareness of our place in the cosmos. We are tiny observers in a vast theater of gravity and light, where titanic forces coexist peacefully, guiding the structure of galaxies while leaving space for quiet contemplation and cosmic appreciation. Black holes as cosmic chronometers. Think about black holes as the universe's clocks, marking the passage of cosmic time in ways subtle yet profound. Their formation, growth, and interactions offer a timeline stretching billions of years, allowing astronomers to trace the history of galaxies and stars. By studying black holes, we can glimpse the sequence of events that shape the Milky Way and distant galaxies. Their slow evolution mirrors the patience of cosmic processes, reminding us that the universe operates on scales far beyond human lifetimes. Reflecting on black holes as chronometers encourages a gentle perspective on time itself. They measure not in minutes or centuries, but in millions and billions of years, teaching us to appreciate the quiet persistence of the cosmos. In this way, black holes are not just objects of mystery, they are the silent keepers of time, guiding our understanding of the universe while allowing us to rest in the calm constancy of their presence. What black holes teach us about time? At first glance, black holes may seem like mere voids in space, yet they offer profound lessons about time itself. Near a black hole, the flow of time stretches and slows, bending in ways that defy everyday experience. Seconds for an observer close to the event horizon may feel like years to someone far away, a gentle reminder that time is flexible, not absolute. This cosmic stretching encourages reflection. We live in a world where minutes and hours often feel fixed and fleeting, yet the universe reveals that time is a fluid, malleable force, intimately connected to gravity and mass. Observing black holes teaches patience and perspective, showing us that what seems urgent in our small corner of existence is merely a ripple in a vast temporal sea. Time, in the shadow of these silent giants, becomes an artful concept, curved, relative, and deeply interconnected with space. Black holes remind us that the universe moves to rhythms far beyond human comprehension, inviting a gentle meditation on the meaning of moments, ages, and eternity. Black holes and the birth of the universe. Here's something to ponder before sleep. Black holes hold clues to the universe's earliest moments. The first stars collapsed, creating the seeds for supermassive black holes that would anchor galaxies, hinting at the processes that shaped cosmic structure. These primordial black holes, if they exist, might carry echoes of conditions immediately after the Big Bang. Their very presence speaks of beginnings, chaotic, energetic, and yet profoundly ordered. Each black hole, formed in the infancy of time, acts as a quiet witness, a testament to forces that set the universe on its grand, unfolding journey. Meditating on this connection brings a calming perspective. From the explosive birth of the cosmos to the slow, deliberate growth of galaxies, black holes remind us that beginnings are often hidden and subtle, yet they shape the vast, serene expanse we observe today. Even in their darkness, they illuminate the story of creation in a soft, reflective way. The link between black holes and the Big Bang. Think about the Big Bang, that silent, explosive birth of space and time. Black holes, in many ways, are the opposite yet complementary. Regions where space is compressed, drawing everything inward. Studying them offers insight into the universe's infancy, the rules governing matter and energy in extreme conditions. These cosmic anchors allow scientists to probe the nature of singularities, density, and gravity, echoing the conditions of the early universe. Through observation, we glimpse connections between the birth of everything and the extreme phenomena that continue to shape galaxies. There is a soothing symmetry in this thought. Creation and collapse exist together, forming a cosmic balance that is quietly eternal. Reflecting on this duality encourages a sense of calm wonder. The same universe that began in a burst of expansion also nurtures the mysterious, concentrated giants we call black holes. Both are part of a cosmic rhythm, a dance of beginnings and endings that carries the universe forward in gentle, enduring harmony. Black holes in popular culture and myth. Here's something surprising. Black holes have inspired myths, stories, and imagination throughout human history. Though their formal discovery is recent, the idea of invisible forces, consuming darkness, and portals to other worlds has long captured the human mind. From science fiction to ancient storytelling, black holes symbolize mystery, power, and the unknown. They are cosmic mirrors reflecting our curiosity, fears, and fascination with forces beyond comprehension. Even as scientists study them rigorously, their poetic and cultural resonance persists, offering a gentle bridge between rigorous knowledge and wonder-filled contemplation. Considering this intersection of myth and reality can be profoundly calming. It reminds us that human curiosity is an extension of the universe itself, an echo of cosmic forces reflected in stories, imagination, and quiet reflection under starlit skies. Black holes, both real and symbolic, invite meditation on the unknown with a gentle, patient curiosity. Why black holes fascinate the human mind. Finally, think about why black holes hold such enduring fascination. Perhaps it is their mystery, their hidden power, or the way they bend reality itself. Perhaps it is the reminder that even in emptiness, there is structure, depth, and beauty. Our minds are drawn to them, seeking to understand forces beyond everyday experience. Yet even without full understanding, they inspire awe, a quiet, reflective awe that encourages introspection and wonder. In contemplating black holes, we explore limits, possibilities, and the infinite unknown, gently expanding our perception of reality. The fascination is calming rather than alarming. It reminds us that curiosity is a gentle companion in life, a patient guide through the darkness, encouraging us to ponder the cosmos without fear and to embrace the serenity of mysteries that are vast, eternal, and quietly present.